Hello, everyone, and welcome to the inaugural Physical Review Letters Journal Club. My name is Kyle Welch. I'm an associate editor for Physical Review Letters. The goal of this series is to highlight outstanding work published in PRL and to provide the authors of the work, especially those who are early career scientists, an opportunity for discussion with the community. It bears mentioning that today's journal club, which is the first in the PRL series, has had the most registrations so far of any of the journal clubs held by the APS journals. And we would like to thank all of you for your enthusiasm. The topic of today's presentation will be a paper that was published in PRL last year, long-range anomalous decay of the correlation and jam packings by Paolo Rissone, Eric Corwin, and Giorgio Parisi. And today's presentation and discussion will be moderated by Ludovic Berthier. There we go. Okay. The topic of today's, before we get started, I wanted to take this opportunity to note that, as I'm sure most of you know, Giorgio Parisi was recently honored as one of the recipients of the 2021 Nobel Prize in Physics. And the paper that we'll be hearing about today was cited as part of the body of work for which the prize was awarded. PRL has a long history of publishing work that goes on to win Nobel Prizes. And in fact, 2021 marked the 11th consecutive year that a PRL was cited by the Nobel Committee. Okay, just a few mechanical things before I hand this over to Professor Berthier. By now, I'm sure everyone knows their way around Zoom, but just in case, please make sure that you are muted unless the moderator calls on you. We're going to hold questions until after the talk. And at that time, you can either raise your hand, the raise hand button can be found in the participants pane, or you can also post questions in the chat. And you can post questions in the chat at any time. We'll just hold those questions for the end of the talk. And with that, I will introduce our moderator, Professor Berthier. Professor Berthier is a CNRS research director at the University of Montpellier, and he is also one of the principal investigators in the Simons collaboration on cracking the glass problem. His expertise includes a broad array of topics in non-equilibrium systems, disordered materials, glassy physics, and soft matter, so we are very happy to have his help in moderating today's discussion. And with that, I will attempt to stop sharing my screen. And I will hand it over
to
Berthier.
Thank you, Kyle. Welcome, everyone. So I'm the moderator of the talks. Paolo Rissone will first give a talk for about 15 minutes, and then we'll start the question and answer sessions. You can raise your hand, write it in the chat any moment. I'll try to organize the questions as they come. So please, Paolo, can you try and share your slides, and then you can start your presentation.
Okay, yes, thank you, Professor Berthier.
So yes, just share your thing.
Yes, just 1 second. And okay.
And put it full screen, perhaps.
It is full screen. Yep.
Okay, that's perfect. Then go ahead, Paolo. Thank you.
So first of all, I would like to thank the organizing committee for inviting us here to give this presentation, and well, all the participants for being here. So as the title of our work says, we studied the behavior of the correlation function at long range in jam packings. But what are jam packings, and most importantly, what is jamming? So in order to understand this, let me first introduce what an amorphous solid is. So this term names a broad family of very different systems, most of which are very common in everyday life. I'm talking, for example, about marbles and pebbles, but also about glasses and powders like the pigment here in the picture, and even about large crowds of people. So what all these very different systems have in common is the fact that all of them are made of disordered particles with no long-range periodicity. In contrast, for example, with the geometric structure of crystalline solids. So how these amorphous solids form, and what are their main features? In the last few years, answering these questions opened a complete new field of research. And in particular, there's been a rising interest in studying and understanding a phase transition that only takes place in amorphous systems, the jamming transition. Then what is jamming? So it happens that if an amorphous solid is compressed, or to say it properly, if the one increases the ratio between the volume occupied by the particle of the system and the volume of the system, the so-called packing fraction, it exists a threshold above which the particle of the system get in mechanical contact between them, so that each particle gets caged by its neighbors and it gets trapped in a fixed position forever. So above this critical point, the system enters the jammed phase. Understanding the jamming transition in general means understanding, for example, how the interactions propagate through the system and what are the main features of the jammed packing. In particular, we are interested in finding all those observables that exhibit a unique behavior approaching the phase transition, as for example happens for the magnetic susceptibility that diverges at the phase transition. So in this framework, it has been hypothesized but never directly measured that the correlation function in jammed packings should go to 0 in the long range as a power law and with a critical exponent equal to 4. This is the so-called hyperuniformity condition. We tested jammed packings for this behavior of the correlation function. To do this, we simulated 96 jammed packings of approximately 16,000 frictionless hard spheres in 3 dimensions. The particles interact via a potential that only depends on distance, and as they are hard spheres, meaning that are non-deformable, the minimum distance between 2 particles in contact is 1 particle diameter, the sigma. So now we know what jamming is. We have our jammed packings to study. What we need next is some tool to probe these systems. So for those that are not familiar with it, let me briefly introduce what the radial distribution function is. So given reference particle in the system that is marked in red here in the picture, the radial distribution function counts how many particles falls in a shell of thickness dr at a distance r from the reference particle. So in other words, this correlation function measures how density varies with increasing the distance from a reference point. And of course, this variation will depend on how the particles are arranged in space. However, there are some limitations and the measure we can get with this correlation, especially when we are trying to look for very weak signals as we are. One limitation is due to the statistical noise that may mask the signal we are looking for, and the other one from the so-called finite size effect, meaning that if you are looking for something in the long range at the limit of your system, you need a very large number of particles. So we overcome these limitations by introducing a new system representation based on the contacts between particles. In fact, given two spheres in contact, their contact point can be represented as a fictive sphere having half the diameter of the original sphere. In this way, we were able to work with a system that for all practical purposes had 6 times the number of particles of the original system and obtain in this way more accurate measures. So to give you an idea of the advantage of working in this context-based representation, we studied the radial distribution function and compared it with the one computed in the original system, let's say, and this is this dashed red line. So of course, all the features shown by the correlation in the original system are also shared by the correlation in the context-based representation, but the latter also gives us more detailed information about the different configurations of particles in contact. So of course, both the correlation features all this configuration that are more common. I'm talking about the one that are a multiple of the particle size. So here, for example, at 1, 2, and 3 diameters. But only in the context-based representation, we are able to reconstruct more complex configurations, like this one at 1.4 diameters and this square root of 7 diameters. So if these are the improvements we get for the radial distribution function in the short range, let's now see what happened in the mid and long range. So here in the context-based representation, we were able to see that the correlation function is actually due to the superimposition of two oscillating functions. One that propagates in the mid-range, and well, it also decays in the mid-range, and that is much faster with a faster period, and another one that is lower and that it reaches the long range. So interestingly here, both the damping coefficient and the period of the oscillations in the mid-range are double those one in the long range. But also important to see that there is no evidence, even in this context-based representation, of an anomalous decay taking place at long range, meaning that maybe the density correlations are not a good observable for testing the hyperuniformity condition, and that therefore we have to look for observable other than density. Therefore, we define a correlation function for a generic observable just by multiplying each term in the summation of the radial distribution function by the value of that observable. So note that we also introduced control parameter S that allows to tune the strength of the interaction. However, there's a problem, let's say, with this definition. And this comes from the fact that this correlation gives information both about the desired observable and the density correlation, as this term is contained in the definition itself. So to filter out this contribution, we divided this function by the radial distribution function that I defined before. That what it actually is obtained just by putting this parameter to 0. And so what we eventually study is this function here. And we computed it for two different observables: the forces exchanged between particles in contact and the number of contacts of each particle. So let's start from the first one. In general, the forces exchanged by particles at jamming form a very complex and unique network that spreads through the system. To give you an idea of such network, here I borrowed this beautiful picture by Bob Behringer from Duke University. This is actual experiment, by the way, obtained by compressing up to jamming bidimensional disks. But anyway, from this picture, is it clear that the forces can be split in two families. There are the strong forces that are exchanged by particles that are almost centrosymmetric, and that form this bright backbone that spreads through the whole system, dividing it into subregions that are the darker one, within which the exchanged interactions are much weaker. So we want to focus, we want to study the correlation of these weak forces, but how can we just select the weak forces and discarding the strong forces? So to do this, it comes in our help that control parameter S we define here in the generalized correlation function. In fact, by selecting only negative values of S, is it possible, we are weighting more the contribution of the weak forces. In fact, here, when S is negative, the weaker the force, the larger is going to be its contribution to the summation. But of course, different values of S will give different signal for the correlation function. So, for example, for S equal to -1, there is almost no trace of the power law decay at long range. And this can mean two things, or that the weak forces, exactly as the density correlation, are not a good observable for testing the hyperuniformity condition, or that we set our threshold too low, meaning that that our control parameter is basically filtering out most of the forces. It happened that this was the case, and in fact, by selecting a higher value of S as S equal to -1/2, and despite the statistical noise that we see here, we were able to measure a power law decay in the long range that goes to 0 with a critical exponent equal to 4.1, so compatible with the one predicted by theory, that is equal to 4. This behavior of the correlation function is shared by the other observable we studied, the number of contacts of each particle. So actually here we didn't study directly this number, but rather the deviation of the measured number of contacts per particle from the one predicted by theory, from the so-called isostaticity condition that is equal to 2 times the system dimension, so 6 in this case. So what we study here is this quantity delta zeta here, and in this case the correlation function shows, well, and in a much more evident way than the weak forces, a power law decay that in the long range goes with a power law and a critical exponent equal to 3.9. So again, compatible with the one predicted by theory. So to conclude, let me just resume our main results. So we proved that GEM packings satisfy the hyperuniformity condition, meaning that the correlation function of a GEM packings goes to 0 as a power law with a critical exponent equal to 4. And we did it for 2 different observables, the weak forces correlation and the number of contacts per particle. Moreover, we introduced new system representation based on the contact point between particles that allowed us to work with a larger system and then to obtain much more accurate results. So I end here the presentation. Thank you all for your attention.
Okay, thank you, Paolo, for the short summary of the paper. So we have one question in the chat by Francesco Alfieri. So if you want to unmute and show your camera, then you can ask your question directly, Francesco.
Okay. Hi all, thank you for organizing this, and thank you for the summary of the paper. So I had a question about the GOVAR. Have you thought of modifying it? So right now the GOVAR is computing the distances between the centers of mass of the particles. Have you thought, or maybe in the future, to modify the GOVAR so that you can actually consider the whole volume of the particle in the correlation, and not just a single point?
Okay. No, it's not something we checked until now, but yeah, for sure it would be interesting to see how this correlation change, especially maybe switching from one representation to the other. But yes, we didn't check it.
Thank you.
If I could jump in, I think that the primary thing that doing that would do would be to essentially convolve the GOVAR with the mass distribution of a sphere. And so that might blunt some of the short range behavior and sort of smooth out some of the long range behavior, but I don't think it would change the sort of asymptotic behavior. I don't think you would see the sort of hyperuniformity exponent showing up in the density function if you were to do that.
Okay, thank you both. There is another question by Ahmad, if you want to ask the question directly, Ahmad. Otherwise, Paolo, maybe you want to answer the question, or Eric or Giorgio, you may want to answer the question related to the accuracy of the measurement versus the fluctuations of the function.
Okay. So with the fluctuation, okay, so yeah, sorry, it's in the chat. Fluctuation of the function. What?
I think it's how precise measurements compared to, you have a tiny bit of fluctuation of variation, which is a smooth power law. It's extremely small, deep at large distances. Are you sure that this is just not noise? I think is the question.
This is not, sorry?
Noise.
Well, I can try to answer the question by Ahmad. I think that the fluctuations are not due to measurement accuracy, but just statistical problems, because we had the fluctuation, the measurements were very accurate, and therefore the fluctuation only comes from statistics. That's all.
Okay, thank you. So I see that someone raised his hand. Thomas Russell, you want to ask your question? Unmute and.
Yes, thank you very much. Would you comment on dimensionality and how this enters? So, for example, crowds in the street that you show are two-dimensional packings, whereas powders, etc., are three-dimensional, and what impact that would have?
So, actually we also checked this well, initially we started to check it for other dimensions, so bidimensional layer, for example, and well, of course we at that time we didn't see this anomalous behavior there, but it was true that we came up with this idea of changing the the system representation, and that it was much more evident in that way. But yeah, I don't know
if I can add something.
Yeah.
So I think we would certainly expect this same behavior in higher dimensions. The complication with doing this sort of analysis in 2D is that in 2 dimensions, monodispersed particles, of course, crystallize. And so this fictive representation doesn't really work if you don't have monodispersed particles. Because
I see. So that's a critical component. So in other words, if I take a polydispersed system where I can basically get disorder as opposed to having ordered systems, then the fictive sphere or circle is not going to function properly. Is that correct?
Yeah, I mean, one can still do the construction. What you lose is the ability to say that these fictive spheres are themselves kissing, right? Mm-hmm. So if you think about the triangle that was drawn.
Right. I mean, but could you do this over a limited range of size scale? I mean, if you have a broad distribution, okay, you have to be very concerned about, but if you don't, in your size distribution, you have still a distribution, but the size distribution is really large, you can still have the disorder. So, and I'm curious if, how that would come in, because 2D arrangements are, as you know, easy to observe, either be microparticles and or now nanoparticles. So.
Yeah, I mean, you can certainly try it. Another piece that I believe that Daniel Hexner has done work looking at the hyperuniformity of the contact number, and I think that was in 2D as well. And so I think we would expect similar results in 2D. However, this particular analysis does have issues in 2 dimensions.
Okay, thank you.
Okay, so I'm looking for the hands have been raised. So maybe a broader question while someone will write the next question is, why are you interested into looking at this hyperuniformity? I mean, do you expect that these jam packing should be hyperuniform? Do you expect they shouldn't be hyperuniform? Are you surprised? Why are you doing this after all?
So as I said, in general, here the interest is in looking all those for those feature that really mark the transition to the gem phase. Well, also because it's not that easy to see how when the packing get to jamming. So from a practical point of view, when you're doing the simulation, you have to reach the end of the simulation, and then you are not sure if the system is jammed or not. So you need to check system, well, yeah, configuration by configuration. And well, this is also why we ended up with this awkward 96 packings in the end, because not all of them get jammed eventually, and it would be nice to have some observable that you can just with which you can just probe your system and say, okay, I can see this, and I know that from this result that the particle is the system is jammed.
So I can also try to answer that, and maybe Giorgio can as well. To me, one of the really fascinating notions of hyperuniformity is this idea that it implies some kind of a long-range organizing principle. And so the result seems to be that in typical jammed systems, you do have this long-range organizing principle in the network of the packing, as shown both in the network of small forces and in features of the network like the contact number. However, you don't have it in the density of the packing. You don't seem to have this long-range organization principle in the density of the packing. And I think that suggests that there's still something, even though we've found sort of the zero energy configuration, this threshold, there's still some fundamental disorder that's present within it that is keeping the density fluctuations present, that's not allowing them to damp out. And yet you do have this long range order in the network. And I think that's a really interesting result here, and something that I think we need to explore more.
Okay, thank you. So there is a question by someone called Yux1 in the chat. So maybe you can ask your question, please.
Hi, thank you. I have a question that I see the weak force definition, and there's weak force and strong force in the whole contact network. And I'm a little bit confused because I read a paper from Rajai, and they defined a strong force as if a contact force is larger than the average contact force of the whole contact network, they define it as the strong force. But then when I look at your paper in PRL, I found that the weak force is kind of it's more similar to a force that connected to a regular contact network. So I don't know if I understand your definition correctly, and this is the first question. And the second question is there any difference between your definition and Rajai's definition, or how to say that, or why we use this kind of definition for the strong and weak force contact network? So thank you.
So yeah, thank you for the question. So actually, in general, the force network has been studied, and basically the forces follows two different. Most of the forces follows two different distributions, and on one side you have, and this is I think the main division between how these two types. Family of forces are split based on the distribution of the forces that you get. I think that there's a paper. I I don't remember. It's by Professor Berthier, I think.
Thank you. Yeah.
Yeah. No, but yeah, it's just study of the forces distribution. And then, well, actually, what we did here is just using the fact that weak forces will be weighted more by assuming this negative value of S, without taking much into account the actual distribution. Well, actually, we did, because we then assumed some limits on the value of S we could take, but I think the division eventually comes kind of naturally from the definition of the correlation function we used.
Okay, thank you. So there was a question related to phonons, which I can answer. The measurements are done at 0 temperature, so temperature plays no role. Then Rajesh, you want to ask your question about softness yourself?
Yes. Thank you for this very nice talk. So I just had a question about, if you were to make the particles a little softer, like in real experimental systems, do you believe these findings will carry over? And what role does that have to play at all in your scaling experiments that you find?
So here I'm happy to pass it to Eric. I am.
Well,
Sure.
I can try to answer. It's clearly that if you, I mean, it just adding to some parameter is, I think that if you put a soft particle, or the fact that the force is soft will place as some kind of cutoff at large distance. But this is, I mean, this is just a pure guess. What you have in reality, one has to really do the computation and to see what happens, because we don't know. The point is that at the present moment, we do not have any fundamental principle for which we can derive the 1 or k to 1 or x to the 4 behavior. I mean, something that we see is something that is very happy because it goes with some other type of ideas, but we do not have a first principle derivation. So I think that looking to the case where soft particles are soft, it would be interesting to see. And I think that this is a very nice suggestion, because it's something that we can do very, very easily, because we have just to slightly compress our code. In reality, indeed, the particles were produced by having particles, soft particles becoming more and more rigid in some sense, rigid to precision machine. So it's something that we can do, and it would be nice to see if we how things happen, what happens, and if we see some kind of increase in over density. I mean, over compression will make something some difference. But I think that also maybe Eric has something to do. Say.
Okay, thank you. So Peter Morse, Peter, you had a question about universality, maybe?
Yeah, it's quite related to that last question. And so you've answered, I think, the second part of that, which was to ask what happens if you were to change the different interaction between particles or in sort of the preparation. But also piggybacking a little bit off of the question in 2D, what if you were to change the polydispersity in 3D? How do you imagine that might change the hyperuniformity and the scaling exponents?
Eric, I mean, I mean, it's similar to the previous question. It's something that we should study, because it's something that is clearly not clear to us if this is some kind of a general phenomena which is independent from force distribution. You know, if we know that in the case of jamming is a critical point in some sense, and in the case of jamming, we know that there are some exponent for the gaps for the force distribution, and this exponent appear to be universal, at least in dimension 3 and more than 3. Also, we know there is some from other type of measurement. One can define a response length, and there have been 10 years old, maybe of 7 years old papers in which we're saying that the response length where is going to infinity when you approach jamming. So this lead to the credence that jamming is some kind of a phase transition. The exponent for forces and gaps do not depend, seem to be universal, because as far as we know, they are the same from polydisperse and non-polydisperse. The point that while the response function it can be seen in jamming, and this paper was very interesting to us because we had the first opportunity to see some long range correlation, not in the response. So we have two problems. So I would say that I would expect that some part of the result properly interpreted will survive with a polydisperse, and about the 2 dimensions, that is something that we have to look at.
Yeah. All right. Thank you so much. Yeah.
Okay, thank you. So we had lots of very detailed questions, or maybe some more general ones to continue. Robert, you want to make this remark?
Yes. So first, thank you very much for a wonderful talk. And I just wanted to use this opportunity, since we have a very broad audience here, what you might want to say to some people who are considering entering the field, you know, just talk about your expectations, your excitement about it.
Yeah, well, actually, I started to work about it during the master thesis, and well, it is very interesting to study this. What I found more interesting is that most of people don't even know the difference between, you know, solid and the glass, and I found it very interesting to discover all this as a student, to discover all these properties of something that we really get in contact every day, and well. On the other side, I found it a bit addictive, you know, in the sense that I'm doing a PhD in biophysics. So, and still in my free time, I'm working on this when I can. So yes, it's something I really, well, I have to thank Giorgio for this. And
so maybe Giorgio and Eric, you want to answer the same questions with very different perspectives, perhaps? Giorgio, you want to start?
Well, you see, the point is that the field is extremely interesting, and I would say that it's a field in which we have done an incredible number of discoveries in the last years. Because if you look to the situation of the field 15 years ago, or also 10 years ago, we had this idea of jamming, but now we have many type of new ideas, a new phenomena, new tools to explore. So I think that the field is quite amazing. Now, it's very difficult to give suggestions. That is another story, because in reality, when you do suggestion, you have to do some forecasts on the future, but the future is not also very difficult to forecast. So I could say that from the things that we know, there's something that is very interesting, and also because it clears a lot about the dynamics of glasses and so on. Now, what I think that is very interesting is the precise boundary between standard glasses, jamming, and so on, and how you go from jamming behavior, the type of things that you see in jamming, that you have some kind of let's say, of multifractality or some kind of marginal stability to glasses that are a little far away, that are not marginal stable. And so how this transition happens for the two is something that from one to the other is something that I feel that is very interesting, but maybe I'm wrong. And also I think that this extremely hard problem is how to put the theory to work, because the theory that we know is mostly mean field theory, and we have not computed the correction to mean field theory, especially in a systematic way, especially for jamming. And this is a very hard problem, but I think that is really interesting.
Okay, thank you, Giorgio. What about you, Eric? Can you share a little bit of your excitement?
Yeah, I mean, I want to echo everything that Giorgio said. And I think in addition, for me, the thing that really drives my excitement for jamming and for glasses is the way that it can be seen to all derive from geometry. And not just the geometry of how spheres fit together in space, but it also brings in these abstract high-dimensional spaces. So it's the geometry of the underlying configuration space. And as Giorgio said, the sort of ultrametricity and multifractality of that underlying space. And it's the way in which this very pure notion of geometry translates into the structure of materials that we can feel. That, when you stand on a beach, the reason why you're able to stand on that sand is ultimately about the geometry of space. And so for me, this intersection between this pure abstraction of geometry and the real material physicality is what I find so exciting about this field.
Thank you, Eric. So I see a question. Someone, Richie, you raise your hand. You want to ask your question?
Yeah, hi. I have three questions. First is related to what other observables we could have used apart from coordination number or contact force. It's very interesting that both observables gave the exponent close to 4. So if we could have used something like local volume fraction, would it be a similar result?
Question 1.
So, well, actually, I don't know a priori like this. I think we should really need to look to study these other observables. But I don't know if maybe Eric studied something else or.
So we've looked a little bit at local volume fraction, and I believe that it should have the same correlations as just the point-wise density. I think your broader question is really interesting, to think of what other measurables you could imagine. Certainly one can consider measurables of the Delaunay triangulation and the Voronoi network. One really nice thing about spheres is that they don't have that many features. So you are somewhat limited in the measurables. And I would expect that any measurable drawn from the network should indeed also show this same power law and the correlation, the same -4 power law, but I haven't tested it.
Okay, question two, Richie.
Yeah, so a follow-up on question 1, like for example, if there would have been bidisperse or polydisperse, then the observables, what observables would you observe?
Well, what do you mean, what observables?
Like instead of going with like, because of the change in the size of the spheres, so what other parameters will become important to look at in the same problem?
Yeah, I mean, I've never got the chance to work with polydispersed systems, so this.
Eric?
Yeah, so I think, you know, in polydispersed systems, I think we expect very, very similar behavior. One confounding thing is that the polydispersity essentially convolves with all of these correlation functions. And so it can blunt the sharpness of these measurements. But we certainly can measure them, you know, directly. There are issues with using the sort of the fictive particle construction. We can measure them directly, and I think we see, you know, similar signatures, but much noisier. And so one would need to go to much larger systems in order to confirm that. But I would expect really materially the same behavior.
Okay, so do you really have a third one?
No, now the second question. So there is this statement which I did not understand. So it's like the FLR can be considered as order of 2 correction to the order of 1 mid-range leading term FMR. So what is the meaning of order of 2 correction here?
So yeah, we expanded a bit on that in the conclusion of the paper, meaning that if you would try to write the equation for that, well, the expansion and the hypernetted chain kind, you would get a leading term of, well, order 1, and then a second term if you continue the expansion that will be of order 2, and then probably that's how these two superimposing function had to be looked at. You know, the leading term of order 1, and then the long range oscillations that are the other one. So it's something, well, that should be actually studied better.
So I'm lost in the questions, but go ahead.
The final question. So why the term hyper uniform? First of all, what is uniform here, and why is it so hyper?
I'm happy to field this. You know, so the distinction is, you think of a uniform point pattern, and so if you were to measure the density fluctuations in that uniform sort of Poisson distributed point patterns, you would get that the density fluctuations are normally distributed. So they're Gaussian, and they would essentially, if you drew ever larger circles and asked how many points fell within it, the fluctuations would be governed by the central limit theorem. And so this would be uniform fluctuations. If those fluctuations are damped out by some smoothing mechanism that creates long-range density order, then those the fluctuations decay more quickly, and so are called hyper-uniform because they decay more quickly than uniform fluctuations.
Thank you.
Okay, so about 2 questions in the chat that I think are a bit related, so maybe I'm going to read them. So the first is, does jamming occur at molecular level? So can we carry over something of what you did to molecules? And then the second question is, how do you suggest carry this over to study the long correlations of other phases of matter than fluids, for example? So 2 related questions.
Let me say that we would expect, I mean, if this type of long-range correlation is something that comes here for some particular reasons, because we have already long-range correlations. We know that we have a long-range response function. So as far as we have a long-range response function, we expect that we're expecting that some kind of long-range correlation should be present. And if you look to other phases of matter that are not at the critical point, I mean, we should not expect to have this kind of long-range correlation. On the other hand, we know that the other phase of matter at the T critical point or at a critical point, they are long-range correlations. So we expect to have here long-range correlation, but just for that reason. Of course, the way that we measure correlation is more or less standard. The reason that in this case was difficult was first all to get the sample, because it's not easy to have the configuration at a jamming point. And after, because the correlation were so slowly decaying, so fastly decaying, that it was difficult to measure. But I don't think that something similar should happen in other case, but I don't know.
Okay, thank you, Giorgio, for this final answer. So thank you everyone for the great questions. Then I think Kyle is going to conclude the journal club.
Yes. Okay.
Thank
Well,
you.
so I just want to thank everyone again. Thank the authors for being here to have this great discussion. Special thanks to Professor Berthier for moderating. So going forward, this is going to be a series of journal clubs. We'll be holding PRL journal clubs every month. So the next one will be in April. Look out for the announcement for that journal club soon. It should be coming soon. I already posted it in the chat once, and I'm going to post it again just for convenience. You can go to this link that I posted in the chat to see recordings from of other journal clubs hosted by some of the other journals, such as Fluids and PRX Quantum. So go check that out if you're interested. And finally, I just want to thank everyone for coming and thank you for the great discussion. And I look forward to an exciting series of journal clubs going forward.
Thanks, everybody.
Thank you.
Thank you. Bye.
Thank you. Goodbye.
Goodbye.
Bye.